I'm a weird dog. I don't want to write about that.
Okay, let me go over the calendar for a minute. You guys picked up a packet, and the packet covers the rest of the remaining new material that we're going to cover, which is curve sketching for trig, related rates for trig, and then inverse trig derivatives. So we'll spend today and tomorrow doing curve sketching. Tomorrow will probably be a pretty short class. I just want to do MVT and one curve sketch problem. Tomorrow we'll just continue with curve sketching. And then there's homework tonight, but I'll check this on Friday. Okay, so this is from the packet that you picked up a while ago. It has 2.3 to 5.6, which is all the sections that have trig problems in them. So I think most of you guys should have this. Does anyone not is missing this packet with homework problems? Okay. So. Okay. So this is page 174 and page 183. I think that's going to be from 3.3 and 3.6 in the packet. Tuesday will be remote day, but I will have help session just going over the previous topics, especially trig related rates and inverse trig derivatives. And then Wednesday, Thursday, Friday, and Monday will be test review. If you want to take the test early, you come talk to me. We can schedule a time where you can take the test early. I will give you the test review packet by Monday so that if you want to work ahead and start preparing for the test, you can do that a little early. And what else am I going to say? Oh yeah, a test recovery. So if you want to do test recovery for this chapter 5 test, you don't have to do it this week or next week. If you prefer to just kind of wait until you get done with this unit, that's fine by me as well. So that finals exam week, which is, well, that Tuesday, we're going to take that test. But that final exam week, that Wednesday, Thursday, Friday, those are all half days, but those are all days where any students can come in and just make up any recovery or any makeup that they want for this class. So. Okay. Any questions about our remaining few weeks here? Okay, so let's go to our packet. This is the trig curve sketch worksheet 1. We'll skip 1 and 2. They're all related, but I want to just focus on 3, mean valley theorem, and then we'll do a curve sketch problem. Okay, so number 3. Okay, determine whether or not mean valley theorem applies to the function f of x equals sine of 2x plus x on the interval from 0 to 2 pi. If so, find the value of c as defined in the theorem. Okay, so I wanted to review a little bit mean valley theorem. Make sure we remember the steps. So on page 3 and 4, I put summary sheet of EVT, mean valley theorem, and Rolle's theorem. So let me just highlight a few things here. So mean valley theorem. Okay, so the whole point of mean valley theorem is we want to find location on the curve where this specified guaranteed slope exists. Okay. So the way we start the problem is we always have to make sure that our function is continuous and differentiable, because if we don't have a smooth curve, then we don't have anything to guarantee. So that's the first thing we need to establish. The second thing is we want to use the endpoints that is provided in the problem, and and find the ordered pairs and then find the slope. Okay. I see a lot of students on the previous test where they find the derivative too soon and they start inserting the endpoints into the derivative. We don't want to do that, okay? We want to just spend our time finding the endpoints, x and y values, finding the slope, so no calculus at all to begin with, okay? The first thing we do is define the ordered pairs, we find the slope. Let's say the slope is 2. Then we found one part of the information that we need, okay? We know that the slope that we're after is a slope of 2, or whatever that slope is between the endpoints, and somewhere along that curve, there must be at least one location where there's that slope of 2, and the way we do that is now we go to our derivative. Okay, we go to our derivative, we go to our slope formula, we set the derivative equal to that target slope, and then in return, the derivative will allow us to find that location on the graph where that specific steepness is occurring. Okay. Maybe there's at least one, maybe there's more than one, but at least we can find one location, if not more, where that behavior is occurring. Okay, so we're just going to practice through MVT, but using a trig problem. Okay, so there's quite a bit of work that we need to do before the derivative, and so I suggest that we do all of our work ahead of time before the derivative shows up, because otherwise, if we find the derivative too soon, you may be tempted to do some of the steps that leads into some incorrect answers. So first thing we need to do is establish our conditions. Our sine graph is a nice smooth curve, no asymptotes, no holes, no sharp turns. So we know our conditions are good. We just have to make sure that we spend the time to list them out. Okay, so our function is continuous on the closed bracket from 0 to 2 pi. And our function is differentiable as well. This time it's on the open interval from 0 to 2 pi. That's the required conditions there. And then we want to find order pairs so that we can find slope. Okay, so no calculus, no derivative. We're just going to spend the time to enter the endpoints into the function. The sign of 0 is just 0, right? So think about your unit circle values. And this test is going to be non-calculator, so we're going to do a lot of this work without a calculator here. So we know that sign of 0 is going to be 0. 0 plus 0 is 0. There's our y value. F of 2 pi. Sine of 4 pi. Sine of 4 pi is same thing as sine of 2 pi. Same thing as sine of pi. Sorry, sine of 0, which is all 0. So 0 plus 2 pi, 2 pi. We have our order pairs. Now we can find the slope. Change in y over change in x. Y2 minus y1 over x2 minus x1. So what's the guaranteed slope somewhere along this curve? 1, right? 0 goes away, 2 pi over 2 pi is 1. Okay. So with MVT, if you can get to this point, then I feel like that's going to reduce a lot of mistakes. I see students, they do f prime of 0, f prime of 2 pi. We don't plug anything into the derivative, okay? Okay, now we have the slope that we are trying to guarantee, that we're trying to target. We can move on to our derivative function. Okay, so
Let's find f prime. Okay, so sine of u becomes cosine of u times u prime. X becomes 1. Okay. Okay, so we have our slope formula. Derivative. Let me clean this up. Okay, we have our slope formula. We have the slope that we want to target. So we set them equal to each other, right? So make sure that we understand where that 1 goes. The 1 doesn't enter in for x, right? This is not location here. This is slope. The slope goes in to the derivative variable. So we set them equal to each other. In return, we're asking the derivative to tell us where is the location on the curve where the specific slope of 1 is going to occur. Okay, so algebraically, we're going to try to get cosine by itself, and then we can talk about the trig portion. Okay, so subtract 1 from both sides, we get 0. Divide both sides by 2. Still a 0 here. Okay, so now we're down to this cosine 2x equals 0. We could use double angle identity, but I want to talk about how we can go through this just using inverse trig and not having to rely on double angle identities here. So I want to try to get that 2x by itself first. Let's move this cosine over. I'm going to involve inverse cosine to move that cosine over to the right side. So 2x equals inverse cosine of 0. We're looking for radian measures. We're looking for radian measures where cosine is equal to 0. Okay. So when is cosine going to be equal to 0? Pi over 2 and 3 pi over 2. Okay. So let's do that to begin with. Now the problem that we're going to run into is that these values are going to shrink. And why is it that these are going to shrink? Eventually, we're going to have to what? Divide by 2. So these values are going to shrink. We want all the values between 0 and 2 pi. So just to ensure that we have enough that we're not skipping any, let's go ahead and find some coterminal angles so that when they shrink, we get all 4 quadrants taken care of, right? We want everything from 0 to 2 pi. So if I want to find coterminal angles, I can always just add 2 pi, right? Add 2 pi, or in other words, add 360 to get another version of it past 2 pi. So pi over 2 plus 2 pi is what? Yeah, so pi over 2 plus 4 pi over 2 is 5 pi over 2. Okay, what's 3 pi over 2 plus 2 pi? 7 pi over 2. I'm going to go 1 further, probably more than I need, but it's nice to go 1 up beyond what you think is going to happen, because that way you ensure if it doesn't fit, you know that you've covered everything. You didn't accidentally skip something, right? Okay, so now I want to solve for x. Divide both sides by 2 is the same thing as multiplying by 1/2. Okay, multiply 1/2 through all my possible answers here. So I get pi over 4. Okay, is there any outside my interval here? 9 pi over 4. So I like to go 1 beyond, just so that I have confirmation. Okay, I didn't accidentally skip something because I found everything up to this point. So there's actually 4 locations on this graph on the curve where there's a slope of 1 between 0 and 2 pi. So sine of 2x is going to condense that graph. So kind of imagine this is just is not accurate by any means, but kind of imagine all the my sine curves here. I'm going to see all those possibilities of places where I can imagine where there's slope 1 occurring on the curve. Okay, want to review mean valley theorem. That will show up on the test. So I want to make sure those steps are still clear to you guys. Okay, any questions?
When we found cosine or inverse cosine of 0, is that the same as finding?
That's the same thing as saying, when is cosine of theta equal to 0?
Oh, okay.
Yeah, and then we know it's pi over 2, your pi over 2. Okay, next page. Let's do a full curve sketch problem. That'll be it for today. We'll just do number 4 and we'll stop. Okay, so given the function y equals 2 x minus 2 cosine x on the interval from negative pi to pi, find the interval increasing, decreasing, relative max, relative min. It says order pairs here, but I'm not going to be too worried about it. Let's just find the x values. Intervals concave up, concave down. So we're going to go through first vertical test. We'll go through a test for concavity. We'll create sign lines for f prime, f double prime. We'll find critical points. Okay. All right, so here we go. Right, that interval seems a little bit strange here from negative pi to pi. We're used to seeing from 0 to 2 pi. So I want to kind of give you some reference here. So from 0 to pi would be something like this, right? Where we're trying to sketch the graph in this interval, but we're going to have to stretch on the other direction here. We're trying to figure out what this graph is going to look like in this interval. Okay, so we'll keep that in mind. We'll still find our critical points from a 0 to 2 pi perspective, but we can always add or subtract 2 pi to get our critical points into where we want it to be, right? Because we have these coterminal angles that we can always adjust with. Okay, let's go through our first derivative test. That's where we're going to find our critical points for our potential relative max, relative min. Okay, y prime equals, right? X becomes what? Okay. 2 cosine x becomes cosine x. Okay, the nice thing, there's no denominator. We can just set y prime equal to 0 and just look for our critical points. I'm sorry, I messed up here. Cosine's derivative is negative sine, sorry. Cosine is negative sine, so that's going to produce another negative, and 2 negatives makes positive. So my derivative is 1 plus 2 sine x. Let me clean that up a bit here. Okay, so we're going to set f prime equal to 0, find our critical points. All right, so where is sine going to be negative? Yeah, fourth and third, okay. It's going to be in the family of what function here, or what radian here? pi over 6, right? So we all find variation of pi over 6 in the third and fourth quadrant. What are those going to be? Yeah, 7 pi over 6. Yeah, 11 pi over 6. Okay. Now we see that these are outside our interval, but we just want to kind of put what we know down on paper first, and then we can make our adjustment. This is outside of our interval. We only want to go from 0 to pi, but this is in the from the pi to 2 pi interval. So what can I do to get it into this region that I want? Subtract 2 pi. Yeah, I can always subtract 2 pi and get the same coterminal angle. So I'll subtract 2 pi here. Subtracting 2 pi, same thing as 12 pi over 6, just to match common denominator. What's that equal to? Negative 5 pi over 6. And then 11 pi over 6. Same thing as negative pi over 6. Okay, so we have variations of these third and fourth quadrant critical points that we can put in the proper interval to match our domain. Okay, so now we can place them onto our slope sine line so that we can build our first derivative test. I do have endpoints because endpoints are provided in my domain.
Why'd you subtract 12 pi over 6 again?
Because I'm subtracting 2 pi to get into the interval that I care about.
Okay, gotcha.
Yeah. Okay, so negative pi over 6 is closer to the positive side. Okay, now without a calculator, we may have some trouble deciding or finding a special angle, especially between negative pi and negative 5 pi over 6. But what we're gonna, what I want to kind of assure you with is, if you can find any slope behavior, the problems I give you will always be alternating signs. Okay, so if you can find one to be positive slope, you know the other ones next to it will be negative slope. Okay, so the problems I give you will always be nice oscillating graphs, continually changing between positive and negative slopes. Okay, so that's a workaround for problems that feel difficult without a calculator. Okay, so let's find some critical points that we can test. An easy value between negative pi over 6 and pi is going to be 0. Okay. And then between negative pi over 6 and negative 5 pi over 6, I'll choose negative pi over 2. That feels like an easy value to test. I can't find anything here, at least not without a calculator, so I'll leave that alone. If I can figure these two out, I can figure this one out. Okay. All right, where do I test these points against? Derivative, right? Derivative. Now, later on, if we want to find order pair, we can put it back into the original. But right now, they're going to go into the derivative. Let's do the easy one first, 0. 2 sine of 0 is 0. 0 plus 1 is 1. That's positive, so I know my graph's going to be positive slope. So from here, you could just go back and say, okay, that must be negative, that must be positive. But let's just go ahead and get some practice in. Another way of saying negative pi over 2 that's more familiar to us is what? 3 pi over 2, right? That feels more familiar to us. If I add 2 pi to this, that's same thing as 3 pi over 2. So let's think about this. What's sine of 3 pi over 2? Negative 1. Negative 1 times 2 is negative 2. Negative 2 plus 1 is negative. Okay, so that confirms, right, that we're getting that negative slope. This one's hard to find, but I already told you that problems I give you will be nice oscillating graphs. Okay, what do we expect here? Relative max and relative min. Okay. Okay, practice writing your because statements. Something that I've seen from previous quiz and tests is sometimes I see the way you name these being not quite sufficient. Instead of saying F prime, I've seen some students write the word because the sign changes. That's not clear enough. Okay. Or they see the word it. Not clear enough either. You want to name whatever you're working with. Okay. If you give those vague statements, you won't earn credit. They'll find a way to take off points on AP exams too. So, okay, relative min. Okay, we'll worry about the sketching of the graph later. All right, let's move on to gathering information about concavity and points of inflection. So let's move on to our second derivative function. Okay, so here's my f prime. So let's go one derivative down further. Okay, all right, so 1 becomes 0. Okay, and 2 sine x becomes the cosine x. Yeah. That's the easy derivative there. We can just look for critical points from here. Divide both sides by 2, I get cosine equals 0. Okay, so let's think about our unit circle values. Where is cosine equal to 0? Power 2 and 3 power 2. Okay, good. All right, so that's what we know from our unit circle. Let's make some adjustment here. Are both of them going to be inside the interval? Okay. Is power 2 safe? This one's safe. 3 power 2 is too far to the right. So what can I do to find something? Subtract 2 pi. Now make sure you always subtract 2 pi. We want to find a coterminal angle. So subtracting 2 pi, same thing as subtracting 4 pi over 2, which is negative pi over 2. So now we have 2 critical points that fall inside the interval within our graph. So we can now create our second derivative sine line. Again, endpoints labeled. Again, your concavity will oscillate nicely, but we should be able to find something that we can test in each interval here. Okay. Let's see, between negative pi and pi over 2 and pi over 2, I'll choose 0. That's easy. Between pi over 2 and pi, I'll choose 2 pi over 3. You can do 2 pi over 4 or 5 pi over 6. I like 2 pi over 3 because it gives us a nice cosine value there. And between negative pi over 2 and negative pi, I can choose negative 2 pi over 3. Okay, we'll test against our second derivative function. Start with the easy one here. Cosine of 0 is 1. 1 times 2 is 2, so positive. This is not slope here, this is concavity here, so concave up. All right, 2 pi over 3, cosine of 2 pi over 3 is second quadrant. Cosine is negative, yep, negative times, this is negative 1/2, actually, negative 1/2 times 2 is negative 1. So concave down. Negative 2 pi over 3, that may not feel as familiar, but we can always add 2 pi to make it more familiar. Negative 2 pi over 3 plus 2 pi is the same thing as 4 pi over 3. Third quadrant, cosine in the third quadrant is still negative. All right, how many, what does that tell us here? What can we conclude? 2 POIs, yep, 2 points of inflection, okay. Let's just, I'm not gonna be too worried about the order pairs, but I want us to be able to sketch the graph. That's gonna match the arrows and the shapes that we have, symbols for. But just to get some anchor points here though, I am going to plug in the endpoints into the function just so I can have some starting points, and from there I can sketch the graph. So let's find the order pairs at the endpoints.
On the F double prime of X timeline, are they always gonna be alternating?
Yeah, I'll make them always alternating. Okay, so negative pi here, so insert into the original function, right? I'm looking for some points to plot as a starting point. Negative pi for all the x's. Okay, so negative pi, for graphing purposes, we'll just treat pi like 3, just so that we can just have an easy number to target. So we'll say that's -3. Cosine of pi, or cosine of negative pi, the same thing as negative pi plus 2 pi, which is the same thing as cosine of pi. Cosine of pi is -1. -1 times -2 is +2. Okay, so it's just, we know it's around -1. We can plot that point later. Endpoint, f of pi, back into the original function. The pi is around 3. Cosine of pi is -1. -1 times -2 is +2. So we're going to start at -1 and we're going to end at 5. Okay, so graph is not complete, doesn't have to be completely accurate, but at least we can use the arrows and shapes to kind of build our graph. Okay, so I'm going to go from negative pi all the way to pi. I'm going to start off down at -1. And after all the movements, it's going to end up at pi comma 5. Okay. Again, whenever I have a slope and concavity sign line, I like to do 2 versions of the graph. I like to just do a sketch of the graph without worrying about the curvature and just follow where my graph is rising and falling. Okay, so I know my graph is going to be rising until it hits a relative max at -5 pi over 6. So I'm just gonna, y value is not important to me right now. I'm just gonna give myself a target relative max to go after. So there's my relative max, -5 pi over 6. And then from there, my graph is going to decrease until it hits a relative min at -pi over 6. So right to slightly to the left of 0. And then my graph is just going to continue rising all the way until it hits pi. And I know my order pair at the end is pi 6, pi 5, sorry. Okay, I know there's curvature along the way. And I'm now going to work those in. Okay. So I know there's 2 points of inflection. Again, the order pair, not too concerned about it. But I'm just going to kind of estimate where my graph is going to land, right? So -pi over 2, that's going to be somewhere between negative pi and 0. So I'm just going to just pick a point between where I think is halfway between 0 and -pi, and just highlight that point. That's going to be where I want my point of inflection to live. And then at pi over 2, there's also another point of inflection. I'll pick a point between 0 and pi where I think is potential POI. I'll highlight that point. And now I'm just going to connect the dots with the appropriate curvature. So from -pi to -pi over 2, I want my graph to be what? Get down. Between -pi over 2 and pi over 2, I want my graph to switch over to concave up. And then for the remaining portion, I want my graph to be concave down.
we know that the relative max is in like the third quarter, or could it be higher?
Oh, yeah, it could be higher up. Uh, if we want to find those exact values, we would enter into the function to find those specific y values, but right now I care more about just, can you use this information to sketch a graph? Okay, any questions? Okay, so tomorrow we're just gonna build on this. I just want us to get comfortable with these trig values, working without a calculator. Okay, so tomorrow, nothing new. We're just gonna be working on this. The homework, I'll check on Friday, but it'd be good if you guys wanted to kind of split it up between 2 days. Okay. All right, go and get your phones.
I have a dentist appointment after this period, so I'm gonna,
I do always worry about that. That happens, so it's.